Today we're going to take everything we learned yesterday and put it on the graph. These concepts include zeros of a polynomial, the multiplicity at these zeros, determining what the multiplicity will look like on the graph, the end behavior of the graph, the turning points, and the degree of the function. All of this will lead us to sketching the graph of a polynomial function. So here are the steps that you should follow. You don't specifically have to follow this order, although you'll notice that I always do follow the same order just to be consistent with my examples. But either way, the first thing that you should do is determine the graph's end behavior. Next, you should find the x-intercepts by setting the function equal to 0 and solving the resulting polynomial. Within this step, you want to make sure you identify the multiplicity. Next, you want to find one additional point between each x-intercept. I'm only looking for one extra point here, so if the y-intercept is in between that x-intercept value, then that's fine. You can use that point. So just one additional point between every x-intercept. And lastly, you want to find the y-intercept by setting x equal to 0 and computing the function of f of 0. This will always end up being the constant term, only if the polynomial is in standard form. All right, so right here I have two examples for you, and the next page is also some examples. We don't need to spend much time on these considering they're already graphed for you, but let's just look at the first one. So on the first one, if you were to graph this, hopefully you all recognize that you have a factor of x plus 1, which would tell you that you have a 0 at x equals -1, and right here we have the multiplicity of 2. That's this point right here. And you can see that the graph comes down, touches that point, and it bounces back in the same direction. That's because the multiplicity is 2. So it tells you what to do at that point. Next, we have a factor of x equals -1, which gives us a 0 at 1. And you can see that the graph is going to go right through that point because the multiplicity of that factor is 1. And lastly, we have a 0 at +3. At +3, same thing. This is going to go straight through the point, straight through the x-axis because the multiplicity is 1. So just to label what each part looks like, this is when the graph turns or bounces at the x-axis. And these two are examples of when the graph crosses. So there's nothing to do here. I gave you a few examples that are already completed. You can use these as reference. On the next page, same thing. Here's another example. These are non-examples just because sometimes I notice that students graph functions like this. These are not polynomial functions. Here I provided you a graph that indicates all your different multiplicities and what's happening on the graph. And two more graphed examples. So that leads us to our first example that we're going to do. Again, we're just going to do two of these today, and then the next note sheet we'll do the rest of the packet. So for this first example, we're going to start by finding the end behavior. Now, end behavior is always found when the function is in standard form. Okay, if we're looking for the function to be in standard form, that would typically indicate that we need to multiply all of this together. There is a shortcut, and it's called a power function. You'll notice that I do it a lot on my note sheets. So a power function is when you take every factor and you multiply the first term together. So I'm going to highlight what I'm talking about here. We have our factor of x. We're multiplying this by the factor of 2x plus 3. And we're multiplying that by the factor of x minus 1, but with a multiplicity of 2. So I'm actually going to write that factor out twice because that's what the exponent is telling me to do. I just wrote that factor twice. To find the power function, you multiply the first term of every factor. So the power function is going to be f of x is equal to x times 2x squared is going to, x times 2x is 2x squared, times x is 2x cubed, times x again is 2x to the fourth. That's the first term of your standard form function. And then we don't care about the rest. So this here just saved us a lot of time. We didn't have to multiply these two factors together and then multiply these two and continue that until we're in standard form. All we did was find the first value. And again, that's by multiplying the first term of every factor. So from this, I can see that I have an even degree and a positive leading coefficient. Even degree positive leading coefficient indicates that as x approaches positive infinity, the function approaches positive infinity. As x approaches negative infinity, the function approaches positive infinity. I'm going to come down to my graph, and I'm just going to make a couple marks on here. I know both ends of my graph are facing up. Next, which I listed as step 2, but again, the order doesn't really matter. Next, we're going to find the x-intercepts. So x-intercepts are found by setting each factor equal to 0. Within this step, you want to identify the multiplicity of each factor, and you also want to label what happens or what the behavior is at the x-axis, and that goes along with the multiplicity. So first, we're going to have a factor of x. If we set that equal to 0, we have x equals 0, which graphed on the graph is at 0, 0. The multiplicity here is 1. So we know that at this point, the graph is going to cross the x-axis. Next, we have a factor of 2x plus 3. If we set that equal to 0, we're going to have a factor of negative 3 over 2. If we plot that as a point, it's at 3 over 2, 0. This factor happens once, so the multiplicity is 1, and that indicates that it crosses at the x-axis. And lastly, we have a factor of x minus 1, but we have a multiplicity of 2 here. That tells us we have a 0 at positive 1, plotted on the graph is at 1, 0, multiplicity 2. Because the multiplicity is an even number, it's going to turn or bounce at the associated 0. So it's going to turn or bounce on the x-axis. Okay, next I need to plot these points. So I'm specifically plotting the points that I found as x-intercepts. I'm going to plot a point at 0, 0, plot a point at 1.5, 0, just notice quickly that I just graphed some dashed lines. These are sketches, so just be as accurate as possible, but you can create the increments however you want to. So you can see I just spaced my graph out quite a bit. I need to graph a point at 3/2, 0. And lastly, I need to plot a point at 1, 0. All right, after I plot these points and before I graph the behavior, so the turning or crossing at the x-axis, I need to find some additional points between each interval. So I need to find a point between these two x-intercepts, so it's either going to be somewhere up here or somewhere down here. And then I'm going to need to find a point between these two x-intercepts. So in this case, it's either going to be up here or down here. And I just need to calculate those. So you can pick any value between these. I know that this point is at 0 and this point is at 1. So I'm going to start by testing an x value of 1/2. And you substitute 1/2 back into the original equation. So when I substitute 1/2 into the original equation, I get, or I substitute in 1/2 multiplied by 2 times 1/2 plus 3 multiplied by 1/2 minus 1 squared. And when I simplify this, I have an output of 1/2. So you can just use a calculator, type it into the calculator, get your answer. But I do know that I am going to have an additional point at 1/2, comma 1/2. X value 1/2, Y value 1/2. All right, I just graphed some increments on the y-axis. Again, you can space them out however you want to, but I know I have to plot a point at 1/2, comma 1/2. Next, I'm testing a value between here I just realized something I did. I actually graphed, I'm so sorry. I actually graphed this point incorrectly. It should be at -3/2. I did have it written up here, and I just graphed it wrong, so make sure you fix that. All right, so I just replotted that point at -3/2, and now I'm looking for a point between those two x-intercepts. So I'm going to test when x equals -1. That's right here. If x equals -1, I substitute this into my original equation, and I have -1 multiplied by 2 times -1 plus 3 multiplied by -1 minus 1 squared. When I type this into my calculator, I have an output of -4. This is going to be an ordered pair at -1, -4. So I'm plotting a new point at -1, -4. The last step is to find the y-intercept, which is found when you substitute 0 in for x. You can probably already tell what the y-intercept is because we do have it graphed, but when you substitute 0 in for x into the original equation, your output is 0, so your y-intercept is at 0, 0. And now it's time for the graph. So we need to pay attention to our zeros and our multiplicities, as well as making sure we touch all points. Remember that this is a sketch, so it does not have to be perfect. You just have to hit all points. It might look a little bit different than mine. Your curves might be slightly different. That's totally fine. I like to start on the left side of the graph, make sure my end behaviors are matching what I'm graphing. I know I need to start facing up towards positive infinity. I'm coming down, I'm approaching the 0 at -3/2, and my multiplicity tells me that I'm crossing through this point. Somehow come down, touch your extra point, whether you just make a curve right at that point or you go through it like I did. You come up, we're approaching 0 where the multiplicity is 1, so we cross through, touch your extra point, come down to 1 where it bounces and we head back in the same direction. And once again, make sure your end behavior is correct. All right, now let's take a look at number 2. This is the last one we'll do for today. Number 2 is in standard form, so to start off with finding the end behavior, we are going to have to identify the power function. And that's what we did before, where I had you write out the expression, write out every single factor. So if you have a multiplicity of 2, make sure you write that factor out twice. So x squared is the same as x times x minus 2 times x minus 4 times x minus 5. The power function is when you multiply the first term in every factor. In this case, our power function ends up being x to the 5th. And we don't care about anything else. Because this is an odd degree and a positive leading coefficient, that tells us that as x approaches positive infinity, the function is approaching positive infinity. And as x approaches negative infinity, the function is approaching negative infinity. So on the left side of my graph, it is facing down, and on the right side, it is facing up. Next, I have my x-intercepts. My first x-intercept is x squared. Set that equal to 0. We have x equals 0. This happens twice. That tells us that the graph is going to turn at that point. We have a 0 at x equals positive 2. This only happens once, or the exponent is only 1, multiplicity 1, the graph crosses. X equals positive 4, also exponent of 1, which means multiplicity of 1, the graph crosses. X equals 5, 5 comma 0, multiplicity 1, crosses. I'm going to sketch out my x values. I need to make it all the way to 5, so make sure you can fit up to the increment of 5 on your coordinate plane. Plot these points at 0, 0, 2, 0, 4, 0, 5, 0. We need to find a point between each value, so I need to find a point between these two, and between these two. Remember that when you find additional points, you pick an x value, you substitute that back into the original equation, you solve for y. So I'm actually just going to tell you the ones I picked to save a little time in this video. I'm going to start right here at x equals 1. When I substitute x equals 1 into the original equation, my output is going to be negative 12. So I'm going to have an ordered pair at positive 1, negative 12. The next ordered pair that I found was when I tested x equals 3. That's between my next two intercepts. When I substitute that into the original equation, use my calculator, the output is 18, so I have an ordered pair at 318. And lastly, I tested when x is equal to 4.5. Here the output is negative 12.66. So I have a point at 4.5, approximately negative 12.66. All right, I need to make sure I can graph all of these, so make your increments on your y-axis reasonable to make sure you can graph negative 12 or down to negative 12 and at least up to 18. So I'm actually going to go up by increments of, let's go up by increments of 2 instead of 1. I need to plot a point at 1, negative 12, another point at 318, and the last point at 4.5, negative 12.66. Before I sketch my curve, I just want to indicate, if you do something like this, please just mark it on your graph. So typically we go up by increments of 1, but if you're going to change that to increments like of 2 or something else like I did here, just make sure you indicate it so I can see on your answer key. All right, the last step is to find the y-intercept. And the y-intercept is when you substitute x equals 0 into the original equation. When you do this for this example, your output is also 0, so your y-intercept is at 0, 0. And now we need to graph. So I'm going to start on the left side knowing that I'm facing down. I'm approaching the 0 at 0. And at this 0, the multiplicity is 2, so it hits that point and it turns back in the same direction. We come down, we touch our extra point, we're heading back towards the next 0, which the multiplicity is 1, so it crosses, touches the next point, crosses through the 0 at 4, crosses back through the 0 at 5. I missed that, but that's okay, it's just a sketch. And that's my final graph. Again, these are just sketches, so they do not have to be perfect. Mine are not perfect. Make sure you just hit all points. That's the most important thing. And label everything.
Number 3 is in standard form. It is not in factored form. Standard form is helpful for things like end behavior and the y-intercept, but it is not helpful to find the zeros. So I'm going to start by factoring x to the fourth minus 2x cubed minus 8x squared. So again, in order to find the zeros, you need this to be in factored form. I'm going to start by factoring out x squared. That's the greatest common factor. Left over is x squared minus 2x minus 8. And then I have to think to myself, what two factors multiply to equal 8 and negative 8, and the same two factors that add to equal negative 2. That would be negative 4, positive 2. X squared times x minus 4 times x plus 2. Okay, this here is our factored expression. And this one up here would be in standard form, just to review the different formats. Okay, I'm going to follow the same order that we did in the previous problems. So last class what we did was we started off looking at end behavior. Then we looked at x-intercepts. Then we found additional points between the x-intercepts, and we also found the y-intercept. Okay, you don't have to follow that order exactly. I tend to always go in the same order. You just have to make sure you have all these parts. All right, end behavior. So for the end behavior, you're always looking at the degree and the leading coefficient. And when you do that, you're looking at it in standard form. In the previous problems, we've had to find the power function, but this one's already in standard form. So here we can see that we have a degree of 4, which is an even number. And we have a leading coefficient that is positive. It would be 1. This tells us that as x approaches positive infinity, the function approaches positive infinity. And as x approaches negative infinity, the function is approaching positive infinity. That means both ends of your graph face up. And I'm going to sketch 2 arrows just to indicate that these are the final locations of your graph. Next, we're going to find x-intercepts. And with this, let's find the multiplicity and what happens at that point. Our first factor, x squared, that would be x equals 0 or 0, 0. This has a multiplicity of 2 because the exponent is 2, or that factor happens twice. And that tells us that on the graph it's going to turn at that point. Our next 0 is x minus 4 equals 0, therefore x equals 4. The intercept would be at 4, 0. Multiplicity is 1, and this would cross at that point. Our last 0 would be found by x plus 2 equals 0, therefore x equals negative 2. Negative 2, 0, multiplicity 1. It crosses at this point. If I come over here to the graph, I know I have to make room on my x-axis to fit up to the point 4, 0. So I'm just going to sketch a couple tick marks, going up by increments of 1. I can plot a point at 0, 0. I can plot a point at 4, 0. And a point at negative 2, 0. Now I need to find points in between each one of these x-intercepts. So I need to find a point in between here and another point in between here. You can pick any x value to test, it just has to be somewhere in between. So I already tested points, and between these two here, I picked to test negative 1. And when I tested x equals negative 1, I substitute that back into the original equation, and my output was negative 5. Therefore, I have an extra point at negative 1, negative 5. My next additional point, I tested between here at 0 and positive 4. I chose to test x equals 2. When I substitute 2 back into the original function and I simplify, I end up with an answer of negative 32. Therefore, I have an additional point at positive 2, negative 32. And for the last step, I need to find the y-intercept. The y-intercept is found by substituting 0 in for x. When I test that in the original function, my output is 0, so my y-intercept is at 0, 0. Okay, so I need to fit these 3 points on the graph. Which means I need to fit down to negative 32 on the y-axis. Let's jump down by increments of 10. Remember, we're just sketching. The y-axis is increasing or decreasing by increments of 10. My first point is at negative 1, negative 5. That would be approximately right here. My next point is at 2, negative 32. That would be approximately here. And my y-intercept is at 0, 0, which is already graphed. So I'm going to start on the left side of my graph. I'm going to pay attention to multiplicity, and I'm going to make sure I touch all of my additional points. So I need to start facing up. I'm going to approach the 0 at negative 2, which my multiplicity says to cross. Come down, cross through that point, come down, go back up. I'm approaching the 0 at 0, which my multiplicity says to turn at that point. So I need to come down, I need to hit that point, turn at 0, head back down, make sure you touch your additional point, head back up where I'm crossing at 4, and I'm heading up forever. Make sure your ends of the graph match your end behavior. Make sure at every point the multiplicity matches with what we determined. So here we know that it's crossing. Here we know that the graph needs to turn or bounce. Here we know that the graph is crossing. Also, make sure when you're graphing that you touch all of your additional points. That's why you find them. Okay, your graph does not have to be perfect, it is just a sketch. For the last set of examples, we are asked to write a polynomial based on the graph that's given. So there's a few ways you can do this, or there's a few parts that you can use to do this. But I like to take a look at the end behavior, the number of turning points, and the zeros, as well as the y-intercept, and make sure all of that stuff matches by the time I write my final function. So the first thing that I want to notice is that there's 1, 2, 3, 4 turning points. So based on our description, the number of turning points is always 1 less than the degree. So that would be the minimum degree. Of course, there could be functions with a larger exponent that could potentially have 4 turning points. So I'm just going to make a note. We need to make sure this matches at the end, that we have 4 turning points. So again, minimum, degree of 5. I'm also going to make a note of the zeros. We have a 0 right here at negative 2. If the 0 is at negative 2 and it crosses through the graph, that tells us that the multiplicity would be 1. We have a 0 right here at x equals -1, also multiplicity of 1. A 0 at 0, multiplicity 1. A 0 at 1, multiplicity 1. And a 0 at 2, multiplicity 1. So these are the zeros. It's where the graph crosses the x-axis. Remember, if it had a multiplicity of 2 or an even multiplicity, it would bounce or turn at that point. That doesn't happen on any of these. So once I list my zeros, I'm going to write a potential function. Now this might not be your final answer, it's just a potential graph. I'm going to use all my zeros starting at x equals -2, and I'm going to write them as factors. If x equals -2, then the factor has to be x plus 2. That way when you set it equal to 0 and you solve, you get x equals -2. We have x minus 1. Oh, I just realized I made a mistake. Sorry, this should be -1. I know I said -1, but I wrote +1. All right, so x plus 1 would be that factor. We have a factor or a 0 at 0, so a factor of x plus 0, x minus 1, x minus 2. All right, we need to clean this part up. We would never write x plus 0 as a factor. That's just x. And typically we write x in front of the function. So I'm going to rewrite this function as f of x is equal to x multiplied by x plus 2 times x plus 1. We already moved this x, so we don't need to write that factor again. X minus 1 times x minus 2. Now we have to make sure the y-intercept is correct. So we're going to test the y-intercept, which is when x equals 0, and we're going to make sure that it comes out to be true. If it doesn't come out to be true, then we need to add a multiplier as what we could call our GCF. We need to add a multiplier in front of the function to make the y-intercept match. So testing f of 0 would give us 0 multiplied by 0 plus 2, multiplied by 0 plus 1, multiplied by 0 minus 1, multiplied by 0 minus 2. So this would be 0 times 2 times 1 times 1 times -1, times -2. But right here, no matter what, we're multiplying that by 0, so this comes out to be 0. Now, is our function showing that we have a y-intercept at x equals 0, y equals 0, or 0, 0? So check on the graph up here, and yes, this function does indicate that we have a y-intercept at 0, 0. So this worked out, this is good. That means this here is our final function. Okay, also check before we're done. I should have mentioned this before I highlighted my answer, but also check to make sure that your degree works. So we determined that the minimum degree is 5. That means if we had a power function, we would multiply all of our first terms together, x times x times x times x times x. That would give us x to the 5th plus whatever else. And yes, that means our minimum degree is 5 because the degree is 5. So that checks out. based on what we know about turning points, this graph matches. Okay, so it might be tempting to just find the zeros and just write them down, but you do have to be careful because, for example, this next graph, the y-intercept is going to change your final answer. So you have to do all of the work that we did on the last problem. Quick note, we have 2 turning points. I'm sorry, we have 3 turning points. That tells us that it's going to be an even degree because both ends face down, so they face the same direction. The degree, or the minimum degree, would be 4. We know that because of the turning points. So we'll check that at the end, make sure it comes out to be true. Next, let's list our zeros. Notice that this graph goes up by increments of 1, but it's going down by increments of 2. So pay close attention when you're listing your values. Anyways, we have a 0 at -1, and you can see the graph turns at that point, so we're going to say that the multiplicity is 2. I mean, it comes up, it touches that point, and it heads back, so it turns at the value of x equals -1. X equals 1, multiplicity of 2. All right, if I write a potential function based on my zeros, I would write this as x plus 1 with a degree of 2 and x minus 1 with a degree of 2. I do have to recognize that my y-intercept occurs at 0, -2. So I need to test when x equals 0, and it needs to come out to -2. Zero plus 1 squared times 0 minus 1 squared. This ends up being 1 multiplied by 1, which is only equal to 1. So as of right now, this does not work. And our function, this function that we wrote, cannot be our final answer. So we need to make our y-intercept work. So what can we do to this value right here to get it to match our y-intercept, which is at -2? In other words, what can we multiply 1 by to make it equal to -2? And the answer to that would be multiply this by -2. That would give us the equation of 1 times -2, which is equal to -2. So our final function would be this function here multiplied by -2. And we're going to write that as f of x is equal to -2 multiplied by x plus 1 squared multiplied by x minus 1 squared. You want to double check and make sure that your degree matches. If we were to check our power function, we would multiply the first term of every factor, which would be -2 times x squared, which would end up being -2 times x to the 4th, which matches our minimum degree. So we are all set, and we know this is our final answer. And for this on your own section, I'm just going to bring the answers in from my website, and I'm just going to talk about them. All right, number one, we're sketching the graph of the polynomial, and this polynomial here is given to us in factored form. So in order to determine the end behavior, you need to find the power function, which is when you multiply the first term of every expression. So we do need to pay attention to our exponents and either include the exponents or expand your factors. So what I'm doing right now is I'm writing my expanded function, meaning I'm not including any exponents. Right here, instead of writing x minus 1 squared, I wrote x minus 1 times x minus 1. And instead of writing x minus 2 squared, I have x minus 2 times x minus 2. All right, now I can multiply the first term of every factor to give me the power function of f of x is equal to x to the sixth plus, who cares, we don't care what the rest of it is, we just need that power function to tell us what our end behavior is. In this case, it's even degree, positive leading coefficient, so both ends of our graph face up. Over here, I determine my x-intercepts from my factors. With my x-intercepts, I indicate what the multiplicity tells me to do. So am I crossing at that point or am I turning? You can see I labeled all of those. Between each point, I find an additional point. This allows me to more accurately sketch the graph. I have my y-intercept at 0, 8. And for my final graph, I come down, I approach -2, I cross through that point, I come and hit my additional point, I come back up to -1 where I cross through, I make a turn somewhere, I hit my y-intercept, I come back down to +1 where I bounce, additional point, bounce again at +2, and my final graph faces up in both directions. Remember, this is a sketch, so at this point of my graph, it doesn't really matter what yours looks like. Yours could have come right towards that y-intercept and back down. That's fine. I just sketched this quick. That was the direction my pen was going in, so I needed to make sure I hit all the points. And for number 2, you're writing a polynomial function given the graph. So we're going to start by identifying that we have 3 turning points. That tells us we have to have at least a degree of 4. I identify my zeros, and the multiplicity at both of those zeros is 2 because the graph comes down and it bounces at each one of these points. I write my potential function as x plus 2 squared times x minus 1 squared. When I test my value of 0, which is my y-intercept, I know my y-intercept has to match at 0, 4, which it does, so I know that my final function is going to be x plus 2 in parentheses squared times x minus 1 squared.